Okay. Hello, welcome everyone for Crypto Cafe. Uh, so today, the first talk will be by uh, how do you call it? Nurdaulet.
Yeah.
Yes, Nurdaulet. So he's a PhD candidate in mathematics and statistics at SDU University, where his research focuses on polynomial continued fraction representations of mathematical constants. He's particularly interested in the algorithms developed by Ramanujan machine and their application in discovering new mathematical formulas. A senior lecturer.
I'm not. No.
Huh? So okay, so it's up to you now. Like you can continue with your.
Okay. Hello, everyone. So my name is Nurdaulet, and today I will be presenting one of our recent papers, which is related to log2 representation through the polynomial continuous fractions. So basically, how it's changed. Yeah. So today's outline, firstly, we'll discuss the modern landscape of polynomial continuous fractions or overall continuous fractions, so how it's evolving and what we are doing now. Then I will try to present some of our contributions. So the first contribution is the proven of some conjecture, and the second one is generalizing that conjecture. And the third, we'll talk about the context and future works that will be done. And at the end, we'll have some references. So if you're ready, we can start. So before moving to polynomial continuous fraction, first we should, I think, discuss what is continuous fractions. So this is normally a continuous fraction representation. So here we will have b0 plus kan divided by bn. So this k stands for, I forgot, Kettenburg or something, which is a German representation, German word for identifying continuous fractions. So this is a used symbol, and this is represented as this. So we have b0 plus a1 divided by b1, and so on. So this is normally a generalized continuous fraction. So if instead of a1, a2s for numerators, we will have ones, we will get simple continuous fractions. And if instead of a's and b's, we will get a polynomial function, then we will have polynomial continuous fractions. So generally, why we are interested in polynomial continuous fractions? The first thing why we are interested, because compared to simple continuous fractions, it follows some logic. Okay, since it's polynomial function, it follows polynomial functions, then we can track out the numerator and denominator values. Where in simple continuous fraction, we cannot do that. And compare it to a series, what we can do is that it converges much faster. And even sometimes it may converge so fast that it can be applied to proof of irrationality of some constants. For example, a priori used polynomial continuous fractions and acceleration methods to prove the irrationality of zeta3. So one of the applications, this. So nowadays, why we came up to this topic is related to the recent development of Ramanujan machine. So this project is led by Israeli professors or researchers who are doing work both in computer science and in number theory. So what they're doing is they're trying to find out the polynomial continuous fraction representation of some constants. Okay, so what they're doing, they're just making a numerical search of all of the constants. So how the Ramanujan, Euler, or others was doing a continuous fraction representation, they were solving it by hand and having some logic on their head. But what Ramanujan machine does, it does the inverse thing. What they took a polynomial continuous fraction, or they took any continuous fraction representation. They took an and bn. I think I can go back. They take some polynomials instead of an and bn. Then they reproduce a polynomial continuous fraction and then calculate its value up to some precision. So let's say 20 points. Then on the left side, they try to calculate all the representation of some continuous fractions. And at the end, what they want gonna do is to look if the left side is equals to the right side. If there is happens that left side is equal to right side, what they do further numerical search and make a calculations up to more, if I'm not wrong, 2,000 digits. And this is how the conjecture is made. So first they do some numerical search, then they find it in the constant recognition, and if they are same, now we have a conjecture. And then conjecture is just needed to waiting for a formal proof. So this is where we are interested. We are interested in doing a formal proof of conjectures generated by Ramanujan machine. So what they do some computational conjecture, and what we are going to do is do some analytical proofs of these conjectures. So these are the sum of the conjectures generated by Ramanujan machine. So first three were known already, and the last two until now was unknown, and it's not proven yet. Okay, so it's not proven yet that this continuous fraction converges to that limits. So this is some of the examples of continuous fractions that Ramanujan machine find. They also have another continuous fraction for all over the constants. It can be logarithm, e, pi. They have some continuous fraction representation of zeta 5, zeta 7, and so on. So especially we are interested, what we are going to look is a continuous fraction representation of log 2. So in 2020, there were conjectured by Zhu He a polynomial continuous fraction that 1 divided by 2 log 2 minus 1 is equals to a representation of polynomial continuous fraction representation of this form. So where an numerator takes the form of the minus 2n squared, where bn is equal to 3n plus 3. Okay, so this still remained conjecture. So our challenge was to try to prove it analytically if these two limits converge to a single value. So here we propose two methods of how do we do that, how we did that. So the first one is called direct approach. So what we did, we taken polynomial continuous fractions, and we are trying to solve recurrence relations for an and bn, where an and bn are the, okay, let me first explain that. Right? So an and bn are the nth convergence of continuous fractions. I hope it's fine. Right? Then we try to solve for recurrence relation, and whenever we solved for a and bn, what can we do? We just take a limit of them, and we are done. So sounds easy. Now the second approach was to generalize what we found. So is there another infinitely many solutions so that we can find a family of polynomial continuous fractions for log 2. So what we found, we first started by known series for log 2, then we converted series into continuous fractions, and then we tried to discover some new family of continuous fractions. This was done to find a family identity of our logarithm. So first, what we try to start it by a direct method. So this is our first theorem. So we let our numerator be equal to minus 2n squared, and our denominator be equal to 3n plus 3. And we say that this identity holds. Okay? In order to do that, what we need to do is a simple thing. First, we need to show that this recurrence relation holds, and we just need to solve it. So sounds easy, right? Yeah. Okay, so before that, what can we do? How can we solve this? So pretty easy. We try to find a closed solutions for both an and bn, and this is our initial conditions. And overall, this recurrence relation was proposed late back by Euler and Wallis. And first things that we do, we try to compute few first terms of an. Okay, so what we are doing, we are just computing few terms of an and trying to find it using OAS, or Encyclopedia of Integer Sequences. Luckily, we found something, and it matches the sequence denoted by this number. Who knows? So it turns out that this sequence is given by this formula. And now what we need to do, we need to just make a formal proof it by applying induction. So we applied induction, and it turns out that our polynomial continuous fraction and an follows this function. Yeah. So seems pretty easy. What we should do now, do the same step for bn, and then we are found, right? Yeah. Here is the hard thing that we found out that for bn we don't have such series, or we don't have such function. Yeah. That was a little bit hard. So that's why what we did, we proposed a so-called educational guess or educated guess, and we said let bn be equal to an multiplied by some series of sk. Okay, then what we tried to do, we put this value into our recurrence relation. Okay, got it? So we put it into our recurrence relation, and after some simplifications, we get this value. Okay, this is what we get. We get 2n plus 6 and all over that. So simplifying it more, we turned out to come first order difference equations. Okay, coming to first order difference equations, so it's much easier to solve. Okay, so we find out that our Sn, okay, Sn is equals to this one. Okay, and we found some initial values S0 and S1, and all of these were based on recurrence relations that we talked before. And the only thing that now we should do is to find the limit of an divided by bn. So as you remember, my bn was an multiplied by sum of sk's. So it simplifies, and I need to just find the limit of 1 divided by sum of sk, where my sk is supposed to be this. Okay, and now my task is to find out that the left part, 1 divided by 2 log 2 minus 1, also converges to this limit, or is equal to this limit. So what we have done just the integration, double integration of both sides. So we take a Taylor series representation of logarithm, take double integration from both sides, since we have here log 1 minus t, and we use it 1 divided by 2 as one of the limits. And integrating it, double integrating it, we find out that 1 minus 2 log 2 divided by 16 is equal to this value. So if you do some algebraic manipulation, what can we do? We can move 16 here, then I will get 2 to the power of n minus 1, right? Then I can take minus from both sides, then I will get rid of this minus. So it turns out that this identity and my previous identity are equal. So this is where it's proven. So we proved that this polynomial continuous fraction converges to my logarithmic identity. So far, I think it's good. So after doing that, there was a question. So is this result a unique, or we can find some other polynomial continuous fractions that are also related to log 2? Okay, so doing that, we proposed the inverse method. So what inverse method says? So until now, what we were trying to do, we know the an and bn, and then we were trying to find big an divided by bn. Okay, it's convergence, and based on that, we tried to find closed form solutions, and based on that, finding limit. And so what if we know the an and bn? So what if we know the a and bn? Can we find the coefficients of small a and bn? Okay, it turns out that it's possible. And the theorem 5, which is written in 2019 by Khadrov and Mashurov, shows us a matrix relation of how they're related. So again, from here, what we get is second order linear recurrence relation. So what can we do to find bn and an? We can take the inverse of this matrix from both sides. And then we will get what? 1 divided by some determinant. And we have, solving for this equation, what can we do? We can find out for an and bn. Okay, so solving for that. So it's pretty easy. We thought that it will be pretty easy, but it turns out that it is not. Okay, so to do that, what we need to do, we need to choose an a and bn wisely. Why? Because not all AN and BNs turn out to be a very good polynomial representation of small AN and BN. Okay, so
Can we have a probabilistic way of finding this AN and BN?
yeah, so this is what Ramanujan machine was doing. So they were searching for all over the space. Yeah.
So what I understand, you are trying to find a deterministic way, right?
Yeah. So
But there can be some probabilistic way as well.
there can be, so like, if you can propose a way, I think we can discuss that. And yeah, so what can we do? So finding big AN and BN so that we can easily find an easy linear BN and AN is becoming a very hard. That's why we decided to move from a known series. So mainly SK. So okay, so what we know that, like, also, yeah. So we know that from Peter Bala, we know that log2 is given by this series. Okay, we know that. And from Euler, we know that we can convert every series into continuous fractions. So that's why Kadyrov and Mashurov proposed a theorem that says that for every series, for every convergent series, we can convert it into a continuous fraction, which is equal to this formula. Okay, so don't worry about this formula. We get this from recurrence solution, so it's not that hard. As you may see from here, what we have is -4 multiplied by Sn divided by Sn minus 1. Okay, here we will also have Sn divided by Cn divided by Cn minus 1. This will be a very important point. Okay, again, so what we are doing, again, our theorem number 2, we propose that for any natural number n, we say that this identity holds. Okay, for AN we have 2k, or k plus m divided by 3k plus 2m plus 2. Okay, so these are just some examples of our polynomial continuous fraction. And so what we do, how we do, so again, as I said, we have a series representation of our logarithm 2, and let's say we say that our Sm is equals to this identity. So we take this identity, and we are trying to find the continuous fraction representation of our Sm. Okay, so we are trying to convert it into Sm. So if we can convert it, then the life will be easy. Okay, so we find out the logarithmic continuous fraction for log2. Okay, so then what we do? So we say let Sk be equal to our previous identity. Okay, then as it turns out from the previous formula, if you remember, we had Ck divided by Ck minus 1, right? Yeah, that's why what we get, it turns out that it simplifies very well. Okay, Ck divided by Ck minus 1 simplifies very nicely. So, and if you plug in into theorem number 4, what we will get? We will get a continuous fraction representation of our Sm. Okay, that we tried to do. So from here, what we can see that it's not beautiful, right? Because we have like -2 k minus 1 divided by k plus m. Here we will also have k plus m. So what can we do? We can make an equivalence transformation of our continuous fractions, and doing some equivalence transformation, which is given by this formula, so which is very easy, I see. We find out the new coefficients to be AK and BK. So these are our new coefficients. So it turns out that using these coefficients, I can turn any logarithmic to continuous series into continuous fractions. And we find out a family of continuous fractions given any natural number m. So this finishes the proof. I hope I was able to explain. Thanks. Yeah, nice. So how it was done? So again, so what we have our Sm converted into continuous fractions using some equivalence transformation and doing some algebraic manipulations. We take j equal to k minus 1. It simplifies that our result, or our theorem holds up by this formula. Okay, so for any -1 to the power of m divided by log 2 and a series of some natural numbers, we'll get a continuous fraction representation for that using this formula. So this is what we were done. This is what we did. And there is another method. So for example, one of the methods of how we can find out the families of continuous fractions is called Bauer-Muir transformation. First, it was done by Bauer, and after I think 4 years or 5 years, it was like edited by Muir, and overall we will get a Bauer-Muir transformation. So this is the acceleration method of polynomial continuous fractions. So as I told, a priori proved the irrationality of zeta tree by accelerating its polynomial continuous fractions, and the one way of to do that is repeatedly using the Bauer-Muir transformation. So what it tells, so what's the logic behind this transformation is that we take a continuous fraction, we take the tail of the continuous fraction, so let's say ak divided by bk, and we try to find out a new polynomial that is very close to ak divided by bk, so that it converges to the same value, but we get different polynomial continuous fractions. So in most cases, it is much faster. It is much faster than our previous PCF. So recently, Chen and Liu proved some of the conjectures generated by Ramanujan machine, where the numerator was of a linear polynomial and numerator was a quadratic polynomial and denominator was a linear polynomial, and they proposed a so-called inverse method also. But unfortunately, I tried to do so for a degree of 3 or 4, but it becomes much more harder to do so. So progress up to date. So what we did, we validated a K-Ramanujan conjecture related to log 2, and then we tried to find out the infinite family for that constant, the same, and we used 2 powerful methods to do so. And our current focus, what I'm trying to do, is to find out if there is other series or if there are other PCFs, so that we can find the infinite family of that. So like using Bauer-Muir, it's already a lot of constants that have the families of continuous fractions, and we try to investigate and interplay with some other acceleration algorithms so that we can find out. And again, I think I'm going to try out to apply a method proposed by Chen and Liu to conjectures derived for P and zeta 3. For zeta 5 and 7, it became much harder. So I think that's all. So if you have any questions, please, you can ask.
I have a question. The conjectures that were proved by Chen and Yu, you were saying, so are they related to any specific constants? What kind of constants?
Mostly, like, let's come up here. So it's not both related to constants. It's related to any constants where numerator is quadratic and denominator is linear polynomial. So
What are the conjectures?
So for example, for P, for E, and for I think for log also.
So it's basically okay. So constants that were already known, right?
Yeah. So like they proposed one of the new methods of how to generate an infinite families of infinite family for the specific constants. So like they made some work much easier. Yeah.
Does any of these acceleration method give some results on transcendence results or things like that?
No. So the problem with acceleration method is that, as I told, like Apri used it for zeta 3, and like some big professors in number theory says that it was a luck that he find out such polynomials that can be accelerated in so many ways. But most of the polynomials cannot be accelerated. So cannot be accelerated repeatedly. I mean, okay? So like you can accelerate it once, but if you try to accelerate it one more time, you get problems. What kind of problems is that? That again, whenever you are accelerating, you get a system of linear equations. Okay, so because what you are trying to do, to change AK divided by BK by some other polynomial. Okay, that is very close to that. Okay, very close to that, so that it will converge to the same limit. But finding it is not easy. Okay, so whenever you are trying to solve a linear system of equations, whenever you are equating AK and BK, it turns out that you get contradiction, or you get very messed equations. So that kind of messed equation can be put in the continuous fraction, but it will not be beautiful. So what is the logic of continuous fraction if it's not beautiful, right? So if it's complex, we can use series. Yeah, that's the problem. And also, for example, for P, E, and up to degree n to the power of 6, this acceleration method works well. But whenever you get to the n to the power of 10, whenever we are talking about zeta 5, you get 10 system of linear equations. And finding a coefficient that satisfy all these equations is very hard, I think, or maybe impossible, because we were unable to do that. And also, another problem is that there is no proposed polynomial continuous fraction for zeta 5. So we have one that is generally, so nk plus n minus 1 to the power of k, but that's the only one, and that works for all zetas. Okay, but for zeta 3, for example, we have some different polynomial continuous fraction that can be accelerated, but this is cannot, unfortunately.
Okay, if there is no question, we should thank Nurdaulet for his talk and
Sorry for that.
and we have one more talk after this. So now Alibek is going to talk about his result on complete classification of quadratic irrationals with period 2. So just a quick introduction of Alibek. He's a senior lecturer in the Department of Pedagogy of Natural Science at SDU University in Kazakhstan, a position he has held since July 2023. He's currently pursuing PhD in Mathematics and Natural Science at SDU. He earned both his master's and bachelor's degree in Mathematics and Natural Science from SDU. From July 2022 to June 2023, he was a visiting scholar at Teachers College, Columbia University, where he expanded his expertise in mathematics education and research. Prior to this current role, he served as mathematics program coordinator in the Department of Education at SDU and as a senior lecturer. Earlier in his career, he taught mathematics in secondary schools where he prepared students for mathematics Olympiad. He has also contributed as a jury member for regional school mathematics Olympiads and scientific project competitions from 2018 and 2020. So it's all yours, Alibek. Thank you.
Good morning, everyone. So, as explained my some bio, I'm very new in science, especially math science world. Before I did my all research in educational field, but now just finished my first year. So it will be very, I think, simple presentation. This is the one of our results while we did some literature review with my supervisor. So this is also published in last year, in 2024, 2024. So here we will also talk about the continued fraction, because with Nurdaulet we have same supervisor and we are almost working in same direction. So as he also mentioned, he has the just continued fraction, and my continued fraction is simple version. So yeah, usually we use this instead of writing all that. And some notation here. So here for quadratic irrationals, we are taking the square root d, where d is not perfect square. And here we also will use the Lagrange theorem that irrational numbers, quadratic irrational numbers is continued fraction. Yeah, so quadratic fraction of quadratic irrational numbers are periodic. And by Galois, it has also palindrome, as shown like this. So A0 and A1, A2, dot, dot, and A2, A1, and the last will be double of the integer part, and this is fractional part. Yeah. So as an example, so periodic part is palindromic. So here we will use to prove our problem by connecting to Pell equation, and shortly, what is the Pell equation? I hope everyone is familiar with this. So we are looking for integer solution when d is positive integer and not perfect square. So this is equal to that because they have some same convergent as a p over q. And yeah, they satisfy both their convergence. Okay, so the main.
What was the equation with -1?
So we didn't meet in this problem with -1, but there is some trick like using this formula to solve -1. Like also there is not infinitely many, so it's restricted.
Then get some of them.
Yeah.
Depends on d.
Yeah. So the main question was inspired by Gauran and Cabos. They proved that there is a, so by the way, this is the distance of, distance by distance we mean, as I told, that's the periodic, the fractional part. And so the length, what will, like, if length is 2, so the question was, is there any infinite set of n such that the period will be 2? So the Gauran and Cabos proved that there is an infinite many limit points, and our question was like, what kind of do we have really like for 2 when the period was 2? How many like infinite sets n do we have? So then we found this formula with special condition. So when our n will be in this form by this condition, so all of them will be period 2. So actually I planned to show by my PC that example as well, but okay. As example, like square root 6, square root 20 has the period 2. Yeah, so while we are proving this, we also prove it like the connection between the Pell equation and the period 2 continuous fraction, length of period 2 continuous fraction. Here is the some examples. So they are related because we know that in Pell equation, first we guess the results, then we can define by the Pell equation method other results. So same results we can see in continuous fraction as well. All this has the period 2. So they converge to each other. Also, yeah, actually my talk was about the period 2, but also we found some examples for period 2 as well with this condition. So if it is satisfied and if it will be integer number, then means this has the length period of 3. So yeah, we did it by also check it by numerical computations. So actually, that's it. Very short explanation. So what we did, establish a connection between the Pell equation and period length 2, then prove it that existence infinity many n with period length of period 2, and derived explicit formulas for length when period is 2 and 3. And like our question was like, if we can continue for k, like for every number, can we guess the specific general maybe conditions for other lengths as well? So for now, that's it.
What's your next direction?
Yeah. Like when we did like why it is challenging to doing for also like when we have period 2, we have only one variable, and it's very easy to define. So like a b, yeah? So we have 2 variables, and then it's not hard to find such a numbers. But when we have 3, it also has the only 2 variables. But when length will be 4, we will have 3. So c will be added, and when we have period 5, then we will have also one more plus variable, and it will be more complex to solve, like to find special conditions. But we are like not fully focused on this, but it's like one of the part of our work also doing on this.
How can you get that formula?
This should I show? But actually, I have everything here. So how I can share this? Is there any possibilities?
Maybe you can you use
Let's experiment. Is there, Alibek, is there
HDMI, right?
another equation which is connected to period 3, like Bell equation is connected to period 2? Is there another Diophantine equation?
We didn't check, I think, because this form is very close to Diophantine equation, but others are like a little bit different, I think. So it works only with period 2, yeah.
So maybe, so this is a theory proof, or it just is like numerical proof?
You can switch to the laptop. Switch
This presentation
video
to
over there on
The switchboard there, there's HDMI. Yeah.
Yeah, okay. Oh, did it switch to?
Yes.
Okay.
But the problem is that it doesn't share anymore, right?
So what is the?
Yeah.
With, but you can see, but it's not on.
Do we have people on Zoom?
No, we don't, but.
But yeah, we are recording.
Very cool.
So this is our draft paper. Yeah. So when we say the period 2, this means B to A, and that's continuous. And by substituting, so taking to both sides by adding both sides by A, we assume that we substitute by X, then we can assume that this also will be X, and then we get the quadratic form, this. And then we get 2 roots. And by again taking that X was the A plus square root N, so we get that N is actually equal to this one. And here is some examples. And here is the check it by real numbers. And for 3 as well. So you see in 3, as it was palindromic, it will see the C will become B. So B to A actually, because in solution, yeah, it will become, this C become as a B. In the final, we will have this form. But when we have period 4, then we will have something like this. Yeah, B, C, B, and we will have one more variable, which is more challenging to define. So we tried that, with 5. There was some remarks, but it's not like good results still.
You can show with the camera here because you only have you can probably move it.
I think it is pretty similar. What would we see on Zoom?
This is not
Sharing.
It's
Can I just
on to
this is
PC, yeah, exactly. See you and showing.
okay? I think it's
Just maybe a little bit higher. It's- Francesco, do you see it?
Yeah.
It's
Okay.
no,
Yeah.
but now this is this which is shared.
is it good? Is it
Yeah, no, this is the. You need to
Just
move
mute
it.
yourself.
So no, you're not showing this.
No?
Cool.
Yeah, I'm sharing. Of course, I'm sharing the screen.
Okay. Now at least not only the screen, like there are two things shared. One is the screen and one is the camera. I think you have to go up in on the left.
Mhm.
Yes.
Yes, like that.
Yes, now it's off.
Okay.
Yes.
Okay.
Yeah, I think now you can.
Other questions? Actually, I was expecting like any advices, how to if you have any idea how to continue maybe this work, maybe some other directions, because as I told before, first year, so we need some advices to improve our research.
I was curious, there was like one slide, I think that you showed that was, they had the gamma functions, related, or the
Yeah.
zeta functions related.
That and gamma is also related.
Were those just identities, or did you do some work with those?
The slide where it was shown some fundamental conjecture related to that. No, all this was discovered by Ramanujan machine.
Oh, okay.
Okay, so like first 3 of known were known already by others, and like rest 2 wasn't known, so it's new, but it's numerical. So if you can prove it, they can include it as reference.
I have one question. So, how do you find an application of this?
It's like
Like there should be some application, like otherwise why they why
Oh,
they started to.
For me, still number theory is abstract, so that's.
No, it looks like solving multivariate equations in
Yeah,
some sense. Like there are some easy cases, like where we know how to solve multivariate equations, right? So I'm just curious to see if there are some easy cases where you can just solve it. At least you know some kind of domain where this kind of problems can be solved.
Well, what should be interesting is to see what kind of equation you get in the tier 4 and tier 5. Yeah, because
Okay,
but if you can find already that you have infinitely many families like that where you have then this would give a more like your the result that you were mentioning before that that the periods of the period set of n root t has infinitely many limit points. This could be generalized to in fact every integer is a limit point. Every positive integer like they have period 2, period 3, period 4, and so on. This can be achieved infinitely many of in time.
so I have one question. Is there any constraint where you want to find the roots? Like, okay, I want the real roots, I want integer roots,
Yeah, integer only.
only integer,
Yeah.
because real is easy to solve because of
Yeah,
Newton
yeah,
Raphson and stuff.
Yeah. It's not, yeah.
It's in some sense a form of Diophantine equations, right?
Yeah. So as this is continuous fractions, they should be integer, and all sets should be integers. So that's the challenging bit.
So there is this Coppersmith algorithm, right? Where they show there are some easy cases where if the roots are very close to each other, we know efficient algorithms to solve it. That's
Yeah.
what Coppersmith tried to do. That's why I was thinking. But they all do over finite field, FQ.
Yeah.
Not over
it does
integer.
modular.
Yeah.
Yes.
But I think if you can do it over FQ, there might be a way to lift it over the integers in some way or the other. Like transform the problem to a FQ, like a finite field, solve it when the solutions are easy to do. Like,
but this is not. I mean, this is not. You're not solving an equation here. You're just giving
A special case.
in a special form. And in fact, if you want to show, for instance, that there are
So you can like guess any number which is satisfy the. Yeah, so which is the satisfies this. So they shouldn't be equal to each other, and B should be divisible by 2A. That's only condition, and any integer, and all them will be period 2. So we can like infinitely find this result.
so that what the theorem that we showed is sufficient, and then the necessary condition, right? It's both. So it has to be like this, and anything like this is period 2.
I see.
Yeah. Okay, I guess.
Okay, any questions?
Thank you.
Otherwise, let's thank the speaker.
Alibek and Nurdaulet will
Let's thank both the speakers, and let's come back next week for the crypto cafe next. Okay, start.
Alibek and Nurdaulet, they will be here until next week. If you want to talk to them, in 241.